Assalamu alaikum students. Today we will discuss an important topic in environmental physics, the fluid dynamics and weather systems, with emphasis on atmospheric circulation. We will focus on the basic physical causes of atmospheric motion, especially pressure gradient force, gravity and Coriolis effect. The aim is to understand how air starts moving, how gravity shapes the atmosphere vertically, and how Earth's rotation changes the direction of motion. This lecture builds the fundamentals for the next lecture, where we will study the geostrophic wind, friction, and large circulation patterns. In this lecture, we will treat the atmosphere as a physical fluid system. We will define the main variables used in atmospheric motion, such as pressure, density, temperature, velocity, and height. Then we will study the pressure gradient force as the main driving force of wind, derive the hydrostatic equilibrium equations, and explain the Coriolis effect. We will also write the basic horizontal equations of motion and understand the physical meaning of large-scale motion on a rotating Earth. We are following the book written by Baker and von Grundel. The starting point of atmospheric circulation is solar heating. Earth does not receive equal heating everywhere. Regions near the equator receive more direct solar energy, while higher latitudes receive less. Because of this uneven heating, temperature gradients are created in the atmosphere. Once temperature gradients appear, they lead to pressure gradients, and these gradients drive wind and atmospheric circulation. And ultimately, wind and circulation create weather and climate patterns. The figure suggests that the weather symbols reminds us that circulation is not just an abstract idea, it produces actual weather conditions such as sunny skies, rain, thunderstorm and snow. The last figure on the right shows the atmospheric circulation structure on the planetary scale. So the concept is that weather and circulation begins with unequal solar heating. Before studying atmospheric motion, we must justify why the atmosphere is treated as a fluid. A fluid is a substance that deforms continuously under an applied force. Both liquids and gases satisfy this definition. Since the atmosphere is made up of air and air flows, it expands, compresses, and moves under forces. The atmosphere behaves as a compressible gaseous fluid. The main variables are pressure, density, temperature, velocity, and height. These are the key quantities used in atmospheric dynamics. The table explains why air is treated as fluid because it has mass, it exerts pressure, it flows from one region to another, it responds to forces, and it transports heat, moisture, and momentum. The figure supports this idea. It shows solar heating of the ground, warming of air near the surface, rising air parcels, and cooling and condensation higher up. This is exactly fluid behavior. Air moves, carries energy upward, and changes state as it rises. So the atmosphere is a dynamic physical medium, not a static background. Now we move towards the fundamental mechanics question. What forces act on air? To answer this, we imagine a small air parcel and identify the forces acting on it. This is a standard and powerful approach in fluid dynamics. The main forces listed here are a pressure gradient force, gravitational force, Coriolis force, and frictional force. Pressure gradient force drives motion from higher pressure towards lower pressure. Gravitational force pulls air downward. Coriolis force deflects moving air because Earth rotates. Friction slows the air, especially near the surface. The air parcel diagram is very important. It shows the air parcel with arrows representing different forces. So you need to picture atmospheric motion in exactly this way. Every parcel of air is acted upon multiple forces at the same time. The gravity is important in vertical direction, while pressure gradient and Coriolis are especially important in horizontal motion. Pressure is defined as force per unit area. This means if air exerts a force on a surface, the force distributed over each unit area is called pressure. Atmospheric pressure is not same everywhere. It varies from place to place and it also decreases with altitude. A special change in pressure is called a pressure gradient. In one dimension, the pressure gradient along the x direction is written as curly p by curly x. Now, this derivative tells us how rapidly pressure changes with distance. If pressure changes rapidly over a short distance, then the pressure gradient is large, and a large pressure gradient produces stronger tendency for air to move. Now, this figure with high and low pressure system help us connect the mathematics to weather maps. Closely spaced isobars indicate a large pressure gradient, and that usually means stronger winds. So the first physical cause of wind is the unequal pressure. Now the pressure difference is turned into an actual force. The pressure gradient force per unit volume is written as F of P equals gradient of P. Dividing by density gives the pressure gradient force per unit mass, or we can say acceleration. In components form, this becomes as Ax and Ay along the respective axes. The minus sign is important. It shows that the force acts from higher pressure to lower pressure. Also notice that if density is larger, the acceleration becomes smaller for the same pressure gradient. That means denser air responds less strongly because it has more inertia. The figure shows a high pressure region and a low pressure region with the force arrow directed from high to low. That is the physical meaning of these equations. Now, pressure differences create the driving force behind atmospheric motion. Now, we apply Newton's second law to a fluid parcel. For a particle, we write ma equals the sum of all forces. For a fluid parcel, the same law applies, but the acceleration is more complicated because the parcel moves through space while conditions may also change with time. So in fluid dynamics, we use the material derivative as given, which contains both the partial derivative with respect to time and also the convection part. Therefore, the acceleration of the air parcel is capital dV divided by capital dt. The first term representing the partial derivative with respect to time shows the local change with time at a fixed point. The remaining terms represent a change because the parcel moves into a region where the velocity may already be changed or different. So a fluid parcel can accelerate because time derivative changes or because it travels into a different part of the flow. The figure tells us again that the parcel experiences all these forces together, and Newton's law tells us that the combined effect determines the parcel's motion. Now we apply Newton's law specifically to horizontal motion. Ignoring friction for the moment, the horizontal equations of motions are written as containing both the pressure gradient term and also the Coriolis term. These equations shows that horizontal acceleration is mainly produced by pressure gradient force and Coriolis force. At this stage, we can say that air starts moving because pressure is not same everywhere. The diagram shows that the parcel is placed between a high pressure and a low pressure region. The pressure gradient force pushes the air parcel horizontally, creating acceleration. Later, when we include the Earth's rotation, this motion will be deflected, and you will see that in a minute. So far, we have discussed force and acceleration. Now we must add a conservation of mass. In atmospheric motion, mass cannot suddenly appear or disappear. This gives the continuity equation, that is curly rho by curly t plus a divergence of the term rho v equals 0. For nearly incompressible flow, this becomes divergence of v equals 0. In Cartesian coordinate, this conservation of mass can be ensured by curly u by curly x plus curly v by curly y plus curly w by curly z equals 0, where this u, v and w are the components of v along the respective axes. The physical meaning is important. If air converges horizontally, then to conserve mass it tends to rise. On the other hand, if air diverges horizontally, then air tends to sink. The figures shows this idea clearly. Convergence and uplift are associated with clouds and rainfall, while divergence and downward motion are associated with clear and drier weather. Now we study the vertical direction, where gravity becomes important. Consider a thin slab of air with area capital A and thickness dz. The pressure force upward at the bottom is P times capital A. The pressure force downward at the top is P plus dP times capital A, and the weight of the slab is rho times A times dz into g. Now for vertical equilibrium, the net force must be 0, as suggested by this equation, that is difference of the pressure forces at the 2 points mentioned above equals 0. Now follow these simple steps, one can obtain dP by dz equals minus rho g, and that is the hydrostatic equilibrium equation. The figure of the vertical air column helps us see that pressure is larger at the bottom than at the top. That vertical pressure support balances the downward pull of gravity. After deriving the hydrostatic equation, we can now discuss it physically. dP by dz equals minus rho g. The minus sign tells us that pressure decreases with height. The rate of decrease depends on density. Gravity compresses the lower atmosphere because the air near the surface must support the weight of the air above it. And that is why pressure is highest near the ground than at the greater altitude. The graph on the right makes this very clear visually. So one can say that gravity shapes a vertical structure of the atmosphere through hydrostatic balance. Now we come to another key ingredient of atmospheric motion, that is the Earth's rotation. Because Earth rotates, moving air appears to be deflected when observed from the surface. This apparent deflection is called the Coriolis effect. In the northern hemisphere, moving air is deflected to the right. On the other hand, in the southern hemisphere, it is deflected to the left. A very important point is that the Coriolis effect does not create motion. It only changes the direction of motion that already exists. So pressure gradient force starts the motion while Earth's rotation bends that motion. The Earth's diagram shown here is excellent for explaining this. It helps us see the opposite sense of deflection in the two hemispheres. This is essential for understanding planetary wind pattern and later the geostrophic wind. Now we will discuss the Coriolis effect mathematically. The Coriolis acceleration is defined as AC and given by this cross product of 2 times capital omega with vector v with a negative sign, where this capital omega is the Earth's angular velocity vector and v is the velocity of the air parcel. For large scale horizontal motion, we define the Coriolis parameter f equals 2 times omega times sine of phi, where phi is the latitude. Then the horizontal Coriolis acceleration has magnitude approximately f times v. Now we will explain the latitude dependence clearly. At the equator, where phi goes to 0, the sine of phi equals 0 and therefore f equals 0. Towards the pole, sine phi increases, so f increases, and that is why the Coriolis effect is weaker near the equator and stronger at the high latitude. The figure illustrates this nicely. It shows no Coriolis effect at the equator and maximum effect near the poles. Here we combine pressure gradient force and Coriolis force into the horizontal momentum equations. These are the basic large scale horizontal equations in a rotating atmosphere. The pressure gradient term drive a motion while the Coriolis term deflect it. The diagram shows the same physical story, that is, air is pushed from higher pressure towards lower pressure, but as it begins to move, Coriolis deflection starts to bend its path. The important point is that the balance between these two effects produces geostrophic wind, and that will be discussed in the next lecture. Now let us summarize the key ideas. The atmosphere behaves as a compressible fluid governed by the laws of mechanics. Pressure differences provide the main driving force for the air motion. Gravity controls the vertical structure of the atmosphere through hydrostatic balance. Earth's rotation deflects moving air through the Coriolis effect. The basic horizontal momentum equations combine these ideas into a mathematical framework for atmospheric circulation, and that will be part of our next lecture. Now the assignment part. The first question asks why the atmosphere is treated as fluid. The second asks for the derivation of the pressure gradient force per unit mass. The third question asks for a derivation of hydrostatic equilibrium, which is where the gravity enters mathematically. The fourth question uses real latitude and Earth's angular speed to calculate the Coriolis parameter, so that will connect you with the actual values of the system. The final assignment question is numerical and applies the pressure gradient idea directly. And that's it. Thank you for your attention.